You know, what happens when a rocket engine starts to hum? And I don't mean in a good way. We're about to dive into a fantastic scientific detective story that finally cracked a 40-year-old spaceflight mystery back in 1981. It's a great one. So this was the central puzzle that had engineers totally stumped. I mean, their most advanced models, the best physics they had, all pointed to one thing. Solid rocket motors should be perfectly stable, but they just weren't. So the big question was, why were these incredibly powerful machines humming a tune that, according to all the math, shouldn't even exist? All right, let's start our investigation right at the heart of the problem itself, this strange, ghostly hum. Check out the difference here. It's pretty stark. On the left, you've got what all the acoustic stability models were predicting. Nice, smooth, stable performance. But then on the right, that's what engineers were actually seeing in the data from real rocket tests, a constant, low-level vibration. They called it a ghostly hum, and it was proof that the models were seriously wrong about something. And look, this wasn't just some small rounding error. As the original paper put it, this discrepancy meant something huge was missing from their calculations. A significant source of acoustic energy had been completely overlooked. The physics puzzle was getting really interesting. So this brings us to our prime suspect, a phenomenon that was kind of hiding in plain sight, right there in the chaotic flow of gas inside the rocket. And the suspect's name? Periodic vortex shedding. It sounds a little technical, but it's basically an oscillating flow that occurs when a fluid, in this case superhot gas, rushes past an object. It creates these little alternating swirling patterns called vortices. Now, scientists knew this phenomenon existed, but was it the real culprit here? This might sound really complex, but I promise you've seen and heard it your entire life. It's the exact same physics that makes a thin wire whistle when the wind blows hard. Or think about a flag flapping in the breeze. That rhythmic repeating pattern? That's it. It's just energy being released into the flow in a very predictable way. Okay, so with a prime suspect in mind, two scientists, R. Dunlap and R. S. Brown, basically decided to build an interrogation room to see if they could get a confession. And they did it with this absolutely brilliant, simple experiment. And this is it. I know, it might not look like a rocket, right? But this simple steel tube was expertly designed to mimic the acoustic environment inside a real solid rocket motor. They just pumped nitrogen gas through it to act like the flow of burning propellant. Now, their method was just a beautiful example of the scientific process. First, they pumped the nitrogen gas through the tube. Second, they put two little obstructions, they called them restrictors, inside the tube specifically to try and trigger that vortex shedding. Third, they used incredibly sensitive microphones to just listen. And then, here's the key part, step 4. They slowly and systematically changed the distance between those two restrictors, searching for what they called a perfect beat. And this is where the story gets really good. They were listening, adjusting, and just waiting for that breakthrough moment, hunting for that perfect beat. And there it is, the confession, caught on tape, you could say. On the left, you're looking at the acoustic data when the restrictors were just spaced randomly. It's pretty quiet, right? But now look at the right. See that enormous spike right around 460 hertz? Whoa. When they hit that one perfect distance, the sound inside the tube just absolutely exploded. So what in the world was going on here? Well, it's a phenomenon called resonance. And honestly, the best way to think about it is like pushing a kid on a swing. If you just push at random times, nothing much happens. But if you time your push perfectly, right at the top of the swing's arc, again and again, that same small push makes the swing go higher and higher and higher. The vortex shedding was the push, and the tube's acoustics were the swing. So the absolute key was this. When the frequency of those little vortices spinning off the restrictors perfectly matched one of the natural resonating frequencies of the tube itself, the two forces locked together, and that tiny bit of energy from the vortices got massively amplified by the acoustics of the chamber.
And they even found the culprit's fingerprint. This number, 0.8. That's the critical Strouhal number. It's the mathematical key that finally unlocked the whole mystery, predicting exactly when this dangerous resonance would kick in. This was the proof they were looking for.
So, case closed. They figured it out. But why does a small hum even matter in something as powerful as a rocket engine? Well, as it turns out, the implications were absolutely huge. So the verdict was in. First, vortex shedding was without a doubt the missing energy source. Second, this proved how tiny, seemingly harmless instabilities could be dangerously amplified by resonance into something that could shake a rocket apart. This discovery meant that where you put things inside a motor, like sensors or other components, is just as important as how fast the gas is flowing past them. And all of this knowledge led directly to building safer, more stable, and much more reliable solid rocket motors. And I really want to end with this quote, taken directly from the conclusion of their 1981 paper, because it just sums it all up with such perfect scientific elegance. Thus, an insignificant oscillation can become very troublesome. Talk about an understatement. This whole story of the ghostly hum is just a perfect reminder of how a tiny, almost invisible flutter of gas could threaten a massive piece of engineering. And it really makes you wonder, doesn't it? What other insignificant forces, what other little ghostly hums might be shaping the complex technologies that we all depend on every single day?